Hi, my name is Billy, and I'm going to tell you all about Einstein. Now let me just look at my book for the first part on relativity. Yeah, that's right. Relativity is the study of... Oh my gosh. I have never been able to control the effects of inertia and gravity.
Who are you?
Me? Don't you... Oh, yes, you're just a boy. Well, I guess my name isn't important. Although I would like to introduce you to my friend.
Where is he?
Can't you... Oh, he's hiding again. This is Felix, my unwilling helper.
Well, my name is...
Billy.
How did you...
No time for chit-chat. Now let's just dive into the theories of Einstein and get it over with.
Hey! No way, this is my show, and I'm going to read my book to these people.
Oh, you don't have to bother with any book. You've got an expert here.
Hey! Fine, I'll do it your way. But we're starting with a basic explanation of relativity.
Oh, very well, child. Wait! I think it would be much more useful to begin with the Michelson-Morley experiment. You see, at one time, physicists believed that there was a substance called ether that was sort of a sea that the Earth, the stars, and even light traveled through. It was a way to measure the absolute motion of objects. Michelson and Morley thought that the only way to detect this ether was to shoot two rays of white light, one going parallel to the ether wind and one going across the ether wind. They assumed that the light beam that had to go across the ether wind would take a longer time to return. However, when this experiment was performed, Michelson and Morley found out that no matter what direction the light was going in relation to the ether wind, the lights arrived back at the same instant. This discovery shocked the scientific world, for it disproved many of their theories. Some of the theories that the scientists had were that time and length were absolute. When Einstein heard about the results of the Michelson-Morley experiment, he began to think that the ether idea as a whole was incorrect. Also on his mind was the idea that certain properties in equations should be true in different frames of reference. But then how could light always be constant in any situation if the idea of frames of reference was true? Einstein answered these questions in his special theory of relativity.
That must have been hard to do.
Oh, it was.
What?
The special theory of relativity states that motion, time, and space are all relative, which means they can only be measured in a frame of reference.
What does that mean?
Imagine one morning you walk out of your home and see a giant Coke bottle in your front yard. Now, has the world suddenly shrunk? Or has a friend just played a huge prank on you? You cannot know unless you have something else to compare it to. In that way, size, or space, is relative. Time is a bit harder to explain as it is merely a measure of events. But I'm sure you know that an hour with a girl on your lap seems like a minute, and a minute on a hot stove seems like an hour. In that way, time is relative. Motion is even more confusing. Imagine that there are two spaceships in the cosmos with nothing surrounding them but space. If you were a person in one spaceship, how could you decide if your spaceship was at rest and the other was moving, the other spaceship is at rest and your spaceship was moving, or both spaceships were moving? You truly could not know with your position on the spaceship. You can only make hypotheses on your frame of reference.
Well, if then everything is relative, how can we measure anything?
There is one thing that is absolute in the universe.
What's that?
The velocity of light. In the special theory of relativity, Einstein realized that if the velocity of light was constant in relation to the Earth's motion, it must be constant regardless to the motion of any star, planet, or meteor anywhere. From this, he stated that the laws of nature are the same for all uniformly moving systems.
What about E equals mc squared?
Oh, well, Einstein began to test his new theory, and he found out some interesting things. For example, a clock at a high velocity is slower than a clock at rest. Also, an object shrinks in the direction of the velocity it is going at. Einstein also noticed that objects increase in mass when they increase in velocity. Since he had decided that the speed of light is a constant and a limit, he began to wonder what would happen to an object at the speed of light. He began with the equation m equals the mass of the object over the square root of 1 minus the velocity squared over the speed of light squared. In this equation, he found that mass and energy must be related in some way. This way was the equation E equals mc squared. E equals mc squared is very important because it demonstrates that a tiny bit of mass has a powerful and sometimes destructive energy, like the atom bomb.
Wow. Can I ask a question?
Of course.
I was thinking about the part that time slows down at great velocities. Does that mean if I went for a trip in space, I'd come back in the past?
Not at all. You'd come back in the future. Let me explain. Imagine a pair of twins. At infancy, one of the children is taken into a spaceship for a 2-year journey to a planet at speeds near that of light. Time will slow on the ship, and the 2-year journey will instead seem only 2 months long. When the child returns, however, 2 months older, she will find her sister at age 2. This seems to be a paradox, but since both frames of reference are different, it is possible.
Can I have my book back?
Why?
Well, I thought we were...
Done? No, child, we have only explained a part of relativity. We haven't even touched the general theory of relativity yet.
The what?
Oh, I can hear better than he can. The general theory of relativity states that the laws of nature are the same for all systems, regardless of their state of motion.
I think you said that already about the other theory.
Perhaps. The general theory, you see, expands upon the special theory. The main point of the theory says that there is no way to distinguish between motion produced by inertial forces from motion produced by gravitational forces. This is called the principle of equivalence.
I want to see how you explain this one.
Actually, this is one of my favorite explanations. Imagine that you are in an elevator, falling from the top of a very high floor. Since you are in free fall, you notice that whatever objects you take out of your pocket stay in midair, and if you jump, you will fly to the ceiling, your body obeying the laws of inertia. It would be very easy for you to assume that you are in space, where no gravitational forces are acting on you. Now, let's travel to the cosmos, where you are in another elevator. This time, the elevator is being pulled upward with a great force. Now, when you take something out of your pockets, you will find that they fall to the floor. If you jump, the floor comes up beneath you. The forces you feel are the same as those of gravitation. In both situations, the force you feel and the force truly acted upon you is different. But truly, both gravity and inertia are involved. Gravity and inertia, therefore, are the same thing, but are categorized by a person's frame of reference.
And light is not affected by either gravity or inertia because it's the constant of the universe.
Wrong.
What?
Imagine again the elevator being pulled up through space. This time, a man shoots a bullet through the elevator. Since the elevator is moving, the bullet goes through the other side lower than the first. This is an effect of gravity or inertia. Now imagine that there is a light beam going through that same self-elevator. Again, the beam will exit a bit lower than its entrance due to the movement of the elevator. Since light has mass, E equals mc squared, it can be affected by gravity. To prove this, you will find that during an eclipse, the light from the stars you see are really images of such stars behind the sun, and can be seen because the light bends toward the sun, toward you, an effect of gravitation.
I think I'm beginning to understand. I have another question, though. Did Einstein ever fail?
Well, he spent the last 30 years of his life looking for a united field theory, which he never discovered, more to the lack of knowledge about space than anything.
What was this united field theory supposed to do?
Einstein was looking for an equation that would join the microverse, which is explained by the quantum theory, and the macroverse, which is explained by relativity. If discovered, this theory would be the ultimate in physics knowledge, for it could explain all happenings in the universe. Although Einstein did not find this theory, other scientists are carrying on his search today.
Or perhaps there is no united field theory.
What?
Well, if there was one, Einstein would have discovered it. Maybe there's no connection.
Oh, there must be. I cannot believe that God plays dice with the world.
What did you say?
I'd better be going now. Come, Felix. I hope you have had some small understanding of a small portion of Einstein's ideas.
But I don't want you to go. Who's going to teach me more about Einstein?
Books. Oh, don't look so sad. Everyone has to say goodbye. Whoever has undergone the intense experience of successful advances made in his domain is moved by profound reverence for the rationality made manifest in existence. By way of the understanding, he achieves a far-reaching emancipation from the shackles of personal hopes and desires, and thereby attains that humble attitude of mind towards the grandeur of reason incarnate in existence, and which, in its profoundest depths, is inaccessible to man.
I guess it all just depends on your frame of reference.